Pluto, a remote and enigmatic celestial entity, was formerly recognized as a distinct and valid planet within our solar system. It was regarded as part of the planetary family until more recent, thought-provoking assertions by prominent astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into focus. These distinguished experts have made a shocking statement: Pluto could be on a potential crash course with Neptune. But how could such an event even occur? What might be the consequences of such an immense event? Are we witnessing an extraordinary cosmic oddity, or is there more to this looming celestial event than what initially appears? Join us as we investigate the possible outcomes of a potential Pluto-Neptune collision. Pluto, once classified as a planet but later redefined as a dwarf planet, continues to intrigue and captivate the curiosity of astronomers and scientists within the vast cosmos. Studies by top space researchers suggest Pluto's orbit lies dangerously close to Neptune's. Notable astrophysicists such as Tyson and Kaku have voiced concerns over the potential hazards of a collision between these two celestial objects, which could present a considerable risk to Earth. But how could such a catastrophic event unfold? Pluto's orbit around the Sun is distinct from any other planet in the solar system. It takes an astonishing 248 years to complete a single orbit. This means that, since its discovery in 1930, Pluto has not yet completed even one full orbit around the Sun. However, the intrigue doesn't end there. Pluto's orbit is characterized by a peculiar shape, vastly different from the nearly circular orbits of the major planets. What makes Pluto's path even more unpredictable is its 17 degrees inclination in relation to the ecliptic plane, making its orbit far more erratic compared to other planets. This irregularity introduces additional complexity to Pluto's orbital dynamics. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune. For approximately 20 years in every orbit, Pluto actually crosses inside Neptune's path around the Sun, defying expectations based on their respective positions within the solar system. This raises an obvious question: why hasn't Pluto collided with Neptune yet? The answer lies in the gravitational interactions of other planets within the system. The study of Pluto's orbit began right after its discovery. Initially, astronomers were baffled by its erratic trajectory. Unlike other planets, whose orbits are closely aligned with the ecliptic plane, Pluto's orbital path stood out due to its steep inclination and irregular shape. The mystery surrounding Pluto's orbital behaviors can be clarified by a concept called the three-body problem in celestial mechanics, which aims to understand the movements and interactions of three objects, Pluto, Neptune, and the Sun, under their mutual gravitational forces. It is similar to predicting the future positions of these bodies based on their current positions and how they influence one another. For Pluto, this problem indicates that the orbits of Pluto, Neptune, and the Sun interact in a complex way. Key terms like asymmetric libration, scope libration, and VSK wobbling are crucial to solving this puzzle. Astrophysicists theorize that the reason all planets maintain their orbits is due to a phenomenon called libration. In the case of Pluto and Neptune, when Pluto crosses Neptune's orbit, their relative positions are offset by approximately 90 degrees. This separation is crucial in preventing their orbits from overlapping and resulting in a collision. Moreover, libration refers to the vertical oscillation of a celestial body within its orbit. For Pluto, this means that whenever it comes closest to Neptune or another massive planet, it is positioned significantly above the plane of the orbits, further shielding it from possible collisions. Another critical factor in this equation is VSK wobbling, named after the researchers who first explored how objects move in space. VSK wobbling refers to how the gravitational forces exerted by Pluto, Neptune, and the Sun influence each other's motion. This intricate dance of gravitational interactions helps maintain Pluto's orbit, even when it follows an unconventional trajectory near the Sun. The three-body problem is central to understanding how objects in space interact with each other. It reveals insights into Pluto's motion and helps astronomers understand the gravitational effects on other distant celestial bodies, including stars and planets. Mathematical simulations from the late 1980s demonstrated that, despite Pluto's unpredictable orbital features, its trajectory remains stable, with only slight variations from its original conditions. These characteristics of Pluto's orbit have stayed consistent over extended periods, allowing astronomers to refine their understanding. Later, computer simulations also provided clarity on how larger planets such as Neptune, Jupiter, and Saturn influence Pluto's orbit. Neptune and Pluto's resonance. Neptune shares a peculiar relationship with Pluto due to a 2:3 orbital resonance. Every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance stabilizes Pluto's orbit. However, Neptune's gravitational force is not the only influence. Jupiter's immense gravitational pull also plays a significant role in ensuring Pluto's orbit remains stable. Saturn's gravity also contributes to the stability of the outer reaches of the solar system. Studies suggest that Jupiter's immense gravity is sufficient to ensure Pluto's trajectory remains steady for incredibly long periods, potentially even billions of years. Together, Neptune, Jupiter, and Saturn may be working in harmony to keep Pluto's course on track, preventing disruptions to its orbit. Understanding Pluto's orbit is particularly crucial, especially as there are speculations about a potential collision with Neptune in the far-off future. The complex relationship between Pluto's orbital pattern and Neptune's offers a deeper understanding of how neighboring planetary systems operate and interact. Pluto's case demonstrates how, even in seemingly chaotic orbits, equilibrium can be achieved through the intricate interplay of gravitational forces and orbital mechanics. It also emphasizes the importance of continuous observation and analysis to maintain our place in the universe. The stability of the solar system. The potential for orbital resonance and the critical relationship between Pluto and Neptune's orbits is a key feature of this dynamic. The 2:3 orbital resonance ratio between Pluto and Neptune ensures that, despite their intersecting paths, they never collide. This resonance is an essential component of the celestial puzzle, preventing any disastrous interactions. Additionally, other massive planets, like Jupiter, Saturn, and even Uranus, play a role in maintaining equilibrium within the solar system. Jupiter's immense gravitational pull acts as a safeguard for smaller bodies like Pluto by influencing their orbits and preventing them from straying off course. Some researchers suggest that Jupiter's gravitational force might have even prevented Pluto from being ejected from the solar system altogether. While Pluto's orbit remains stable for now, changes could still happen in the future. Astrophysicists like Neil deGrasse Tyson continue exploring the cosmos, providing a deeper understanding of the delicate balance. The outer planets, especially Jupiter and Neptune, exert long-term effects on Pluto's orbit. Even small changes in Neptune's motion over millions of years could gradually nudge Pluto's path in unpredictable ways. Additionally, beyond Neptune lies the Kuiper Belt, a vast region filled with icy bodies and dwarf planets. Some scientists theorize that an undiscovered large object, possibly a hypothetical Planet 9, could one day shift Pluto's orbit significantly. Another possibility is the influence of passing stars. Over billions of years, stars from other systems occasionally pass close to the Sun, exerting slight gravitational tugs on the outer solar system. If such an event occurs close enough, it could subtly affect the orbits of Kuiper Belt objects, including Pluto, leading to long-term changes. What would happen if Pluto and Neptune collided? Although a Pluto-Neptune collision is highly unlikely due to their orbital resonance, it is still an interesting scenario to consider. If such an impact were to occur, the consequences would be catastrophic, not just for Pluto and Neptune, but for the entire solar system. If Pluto, a dwarf planet roughly 2,377 kilometers in diameter, were to collide with Neptune, which has a diameter of 49,244 kilometers, the result would be an immense explosion, scattering debris throughout the outer solar system. The impact would likely create a vast debris field, potentially forming a new ring system around Neptune. A massive collision could also send large fragments of Pluto hurtling toward the inner solar system. Some of this debris might even reach Earth, appearing as a meteor shower or, in extreme cases, posing a potential impact threat. However, given the stabilizing effects of resonance and the gravitational influence of other planets, such a collision remains purely theoretical. The broader implications for celestial mechanics. The study of Pluto's orbit provides insights not just into our own solar system but also into exoplanetary systems. Scientists examining distant star systems have found similar resonant relationships between exoplanets, offering clues about how planetary systems evolve and maintain stability. Understanding these cosmic interactions is essential for predicting the long-term future of our solar system. Will Pluto's orbit remain stable for another billion years, or will slow, accumulating changes eventually lead to a shift? Could external gravitational influences, such as an unseen massive object in the Kuiper Belt, disrupt its trajectory? For now, Pluto continues its journey along its unique and mysterious orbit, a testament to the delicate balance that governs our cosmic neighborhood. The future of Pluto's orbit and the outer solar system. As Pluto continues its slow journey around the Sun, scientists remain eager to uncover more about its long-term stability and interactions with other celestial bodies. With advancements in space telescopes and computational simulations, astronomers can now predict planetary movements with greater precision than ever before. One of the most significant developments in this field is the use of N-body simulations, complex mathematical models that allow scientists to simulate the gravitational interactions of multiple objects over millions or even billions of years. These simulations suggest that, barring any unexpected external influence, Pluto's orbit will remain stable for at least the next few billion years. However, the outer solar system is not a static place. The hypothetical Planet 9 and its potential impact. In recent years, some astronomers have proposed the existence of a ninth planet, sometimes referred to as Planet 9 or Planet X, lurking beyond Pluto in the far reaches of the Kuiper Belt. This hypothetical planet, if it exists, could be as large as Neptune and might be responsible for the unusual orbits of several distant Kuiper Belt objects. If Planet 9 does exist, its gravitational pull could eventually alter Pluto's trajectory. Even a small shift in Pluto's orbit could have cascading effects on other objects in the Kuiper Belt, leading to potential long-term changes in the stability of the outer solar system. Could Pluto be ejected from the solar system? Another extreme scenario, though highly unlikely, is that Pluto could one day be ejected from the solar system entirely. In celestial mechanics, there is a concept known as gravitational scattering, where a smaller object, like Pluto, experiences a close encounter with a much larger planet, such as Neptune or Jupiter. If such an interaction occurred at the right moment, Pluto could gain enough energy to be flung out of the solar system, becoming a rogue planet drifting through interstellar space. While current models suggest that Pluto's orbit is well protected, a major disruption, such as a close pass by an undiscovered massive object in the Kuiper Belt, could, in theory, destabilize its path over millions of years. The importance of continuous observation. The study of Pluto is far from over. NASA's New Horizons mission provided the first-ever close-up images of Pluto in 2015, revealing an astonishingly complex world with towering ice mountains, vast nitrogen plains, and possible subsurface oceans. Future missions, such as proposed Pluto orbiters or Kuiper Belt explorers, may provide even more insight into its long-term behavior. Continuous observations from Earth-based telescopes, space observatories like James Webb Space Telescope, JWST, and upcoming next-generation instruments will allow scientists to monitor Pluto's orbit and detect any subtle changes that could hint at larger cosmic events in the future. The bigger picture: Pluto as a window into the cosmos. Pluto's unique orbit, its interactions with Neptune, and its place within the Kuiper Belt make it a fascinating subject for astronomers. Understanding Pluto's movements helps scientists refine their models of planetary formation, orbital resonance, and long-term solar system stability. Beyond our own solar system, Pluto-like exoplanets may exist in distant star systems, following similarly unusual orbits. By studying Pluto, we gain valuable knowledge that can be applied to the study of exoplanets and the formation of planetary systems across the galaxy. Conclusion: a cosmic dance that continues. Pluto remains one of the most intriguing objects in our solar system, a tiny world defying expectations at the edge of our cosmic neighborhood. While theories about collisions, orbital changes, and even planetary ejection make for fascinating discussions, the reality is that Pluto's journey is governed by the same intricate gravitational forces that keep our solar system in balance. For now, Pluto continues its steady dance with Neptune, locked in a delicate orbital rhythm that has endured for millions of years, and will likely continue for millions more.